Hello, I'm Dan Olds. I'm the organizer of the Winter Classic Invitational Student Cluster Competition, and I've got a special treat. I've got Jack Dongarra here with me, and he is, in a lot of ways, at least one of the fathers of modern HPC benchmarking, having been one of the originators of the HPL or LINPACK benchmark, and also of the HPCG conjugate gradient benchmark that is much more recent. How are you doing, Jack?
Oh, we're doing well, Dan. Thanks for asking. Yes, everything is good on my side here in Knoxville, Tennessee.
Very good, very good. So can you give us a little overview of HPL?
Sure. So HPL stands for High Performance LINPACK. LINPACK is a LINPACK. Of course, many people think of LINPACK as a benchmark, but it's actually a collection of mathematical software. So back in 1970, probably 1972, 1973, I was involved in a project at Argonne National Laboratory where I was working. And the project was to develop a package of software for solving systems of linear equations. And we called that package LINPACK. And as part of putting that package together, I composed a benchmark to see how fast the software was running and to give users a handle on how long it would take to solve certain problems. So I put together a test which solved a system of linear equations using this LINPACK software. And I chose a matrix that was random, a random matrix. We're going to solve a general system of equations, and I wanted that matrix to fit into all of the computers I knew about at that time. So we're talking 1972. I had a collection of computers that we were using to test the software. And on that collection of computers, the biggest matrix I could store was a matrix of size 100. So the LINPACK benchmark started out by testing some Fortran code on a matrix of size 100 on a bunch of machines. And
it's pretty small.
It's pretty small, that's right. And I sent you a slide deck, and in that slide deck, you'll see, I think it's on slide number 2 of one of those slide decks. I think it's one that's called Perspective. There's a slide which shows all the machines I had access to at that time, ranging from a Cray 1 to a PDP-10, a DEC PDP-10. And again, it was the matrix size was chosen so I could run effectively on all of those machines.
And thus give comparable performance across those platforms.
And it gives a wide range. It does give performance numbers. And so there's a chart there in that that table is a chart that I composed, and there's some handwritten numbers there, and those are my handwritten numbers of the megaflop rates. So the Cray 1 at NCAR, National Center for Atmospheric Research, was running the benchmark around 14 megaflops. That was the rate of execution at that time on that Cray computer. So that was, again, a Fortran code that was using a set of assembler BLAs. And back in 1972, the assembler BLAs that we had were the simple BLAs, the level 1 BLAs, just doing vector operations. And LINPACK was really designed around those vector operations. So the benchmark started from some Fortran code for solving a system of equations. It started on a bunch of handful of machines back in 1972. And I had this table, and whenever a new machine came around, I would run my benchmark and add it to this table. And that table became a report, and that report sort of went on for many years with collecting additional machines and adding to this list of benchmark results.
And that became
the LINPACK benchmark report. And over time, that LINPACK benchmark had to change characteristics. A matrix of size 100 was pretty small. And we changed the size of the benchmark from being just 100. We also included a matrix of size 1,000. So to give two sets of numbers for a small matrix and then for a large matrix. And with the large matrix, we said that you could do things beyond simple Fortran. You can do a better job of optimizing that code, and that was sort of the standard for a long time. And then my colleague in Germany, Hans Moyer, he had a list of supercomputers. And he saw my list of benchmark results. His list of supercomputers ranked the computers by the peak performance, the theoretical peak performance.
Okay.
And he saw my list, and we got together and we decided to have a benchmark based on the LINPACK algorithm that is solving a system of linear equations. And we modified the benchmark so that it wasn't restricted to a matrix of size 100 or 1,000. You can make the matrix as large as possible, as large as you can fit in your computer. So the HPL became the benchmark that was going to be used in the top 500 list. And that benchmark was to solve a system of linear equations, making that system as large as possible. We would measure the time to solve the system and then convert that time to a rate of execution. And what was entered into the table was the rate of execution, the flop rate. So the flop rate was the number that you were assigned for your machine based on running that benchmark. And the benchmark ground rules say that you must, again, solve a system of linear equations where I will generate the matrix. You tell me the size and I'll generate the matrix. And you can use any implementation, but the method that you use must be Gaussian elimination with partial pivoting. So that's a rather standard method for solving systems of equations. You have to use that algorithm, but you can implement that algorithm as best you can on your machine to get the rate of execution, which then would go into the top 500 results. So the top 500 benchmark was started in 1993. So it had a long gestation period of 20 years from the time when the benchmark was first created, that is solving a system of equations of size 100, to the point where we actually had collected 500 machines with those ground rules to come up with this list. And that benchmark goes by the name of HPL, the High Performance LINPACK. It's collected in the top 500 list. It started in 1993, and that list comes out twice a year. It comes out in November and June to correspond to the big supercomputing meeting in the States in November, and the European or the international supercomputing meeting, which is usually held in Germany in June. So that's sort of the cadence of that benchmark and giving you a handle on when it started. So it's been going on for a pretty long time.
Yeah.
1993 till today. So that's a run of somewhat 38 years, I guess, at this point.
We're coming up on 40 in a couple of years here.
That's right. Yes, indeed.
We'll have to do something special for that.
I'm sure. That's right.
Yes. So putting yourself in the place of these student cluster competition teams, what would you do to best optimize and to get the best LINPACK score?
Right. So with LINPACK, of course, the kernel or the operation which is the most computationally intense is matrix multiply. That's the GEM operation. I would recommend people to use the optimized GEM for your architecture. If you're running on Intel, there's a very good Intel implementation of that kernel that should be used on AMD. They also have it, NVIDIA has it, and so on and so forth. So the gem operation is the critical thing. Another important thing to optimize or tune for is the block size. So the block size refers to how big a matrix multiply that's going to take place. And the matrix multiply for this particular algorithm is not a square matrix. It's a matrix which is rectangular. And getting the size of that right and getting the blocking that's done internally is critical for performance. And the way one optimizes is to run a few experiments and to see how well the performance can be tuned to the size of that block, trying to optimize. So one optimization direction is along the lines of getting that blocking correct for matrix multiply. The other optimization, which is critical, of course, is going to be message passing and how effectively messages are passed on the machine itself. And today we have MPI as the standard. And, it's good to experiment with different versions of MPI if you can on the architecture that you have to try to find the best version of MPI that you can to optimize that.
So we're experimenting with different block sizes and then in conjunction with that with different MPI versions as well.
That's right. So those are the two directions of optimization that can be done to enhance the performance of the kernel for that for the HPL run. That's exactly right.
And at some point, when you go too big, you're going to get diminishing returns, right?
Oh, exactly. Yes.
Okay, so you want to find out that inflection point.
You do, and there's another optimization, and that's the logical grid of processes that are used. So there's with the benchmark, we think of distributing the matrix on a logical grid of processes. That's a P by Q grid. And the ratio of P to Q is going to be also important to get right. So experiments should be done to optimize the correct ratio.
That's a new one. I hadn't heard about that one.
So yeah, you want to get that. You want to get that right. So in the rough cut is you're given a machine which has so many nodes on it, and you have to come up with a P by Q. P times Q is going to be the number of nodes that you use, and then the aspect ratio is something that has to be figured out to optimize the performance as well. So that's another direction, I'll say, in the optimization. So it's a more complicated optimization space that one has to work with here.
Yeah, we have a big mix of machines in here. Some are using GPUs, some are not using GPUs, but they're all bound by an 80 teraflop R peak limit.
Right.
And so it's going to be we'll see, but I think it's going to be a fairly wide distribution of nodes.
That's right.
That's going to be interesting, but they've got to have at least two. All of you students out there listening, you got to have two, because otherwise it's not a cluster.
It's not. That's right.
Yes. Well, that's great. Can you now kind of do the same job on HPCG and talk a little bit about why that needed to come about?
Right. So I'll say that there's a lot of good things about HPL. So HPL has a lot of nice features. It's easy to run, fairly easy to understand. It's easy to check the results. We have this big historic database of information going back to
1993. Yeah.
We have good community tools for implementing that, and there's a fair amount of understanding on that benchmark. However, there's some bad things as well. So the LINPACK benchmark has been around a long time. HPL has been around a long time. It really is a floating point intensive calculation. So the way to think of it is if you have a matrix of size n, the benchmark HPL does n cubed floating point operations, and it moves roughly order n squared data. So we have n cubed floating point operations and n squared data. So it's very heavy in terms of floating point operations. However, many applications today don't have that ratio. They don't have that cubed to squared effect, that surface to volume effect, surface of data to volume of floating point operations.
I mean, I kind of think of it as a full-on matrix grid where there's data everywhere.
That's right. And so it's a dense matrix. That's a good way to think of it. And many applications don't have that. They have sparse matrices. And we don't use Gaussian elimination with partial pivoting to solve those kinds of matrix problems. So I'll say that many applications are trying to solve some partial differential equation. And the way that partial differential equation is solved is by a discretization process, which leads to a sparse matrix. And now you want to solve a linear system that has a sparse matrix as its primary component. And we use an iterative technique to solve that, not a direct technique. Gaussian elimination with partial pivoting is considered a direct technique. And an iterative technique takes that sparse matrix and multiplies it by a vector. That's the basic operation that goes on in solving that sparse matrix problem that comes from these PDEs. So now we're faced with a different scenario, not n cubed floating point operations, but something which is more like n floating point operations on n pieces of data. So that's the balance that we have now with the HPCG benchmark. So it really is quite different.
And much more like the types of workloads that we see today.
Exactly. So it's a better reflection of the real nature of applications that we have today. So basically, back in 1973, maybe HPL was a good way to look at doing measurements of computers because floating point was very expensive. Today, however, floating point is not very expensive, and we need to focus more on moving data around on the architectures that we have. So we turn our attention to coming up with a new benchmark. And HPCG is a benchmark which is based on an iterative technique. It does a conjugate gradient method is the basic method that's used as opposed to Gaussian elimination with partial pivoting. And it's working with a sparse matrix as opposed to a dense matrix. So again, the benchmark goes as follows. You're going to solve this matrix problem. I'm going to give you the matrix. It has a very specific form to it, prescribed form, and I can tell you what that is ahead of time. And then you're going to come up with the basic operations. And the basic operations that you have to optimize are doing a matrix times taking a sparse matrix times a vector. That's the basic kernel that has to be optimized for this particular benchmark itself. And there's a preconditioner that's used that's also prescribed, and data has to be passed around since we're working on a cluster, and it becomes an optimization problem again. How you do that sparse matrix vector product and how you pass data around in your cluster.
It's a brutal benchmark, but it's also quick.
Yeah, so that's another, I'll say, facet or feature of the benchmark. One of the problems with the LINPACK benchmark, HPL, is it does take a long time. And by a long time, I mean, we have results that have been submitted, which take over 1 day to run. So over 1 day to solve this matrix problem. And you can't really expect it to run a benchmark to take a day. So we want to be able to solve things quicker. And even on the fastest computer, HPL, for instance, is taking about 4 hours to run. So the fastest computer, let's say the Fugaku machine or the machine at Oak Ridge, the Summit computer, takes a long time to run the benchmark. So when designing this new benchmark, we wanted to come up with a test which would complete in a much quicker time. And we've constructed the benchmark HPCG to actually solve, not actually solve the whole problem, but to solve a portion of the problem and report the results for solving that portion of the problem. And we have a way to verify the solution and to do things so that we can be assured that the results are correct.
Let me just insert here, by the way, students, your LINPACK runs will not take hours and hours. You're running much, much smaller machines. So don't worry about that. So while we're bringing up the students, what should they be looking to do with HPCG?
Well, again, it's again trying to optimize a matrix times vector. We have a sparse matrix times a vector. And the operations that are done there are not a matrix operation, not a matrix times a matrix. It's more vector operation. So the operation that's very common here is an AXP, taking a scalar multiple of a vector plus another vector. So AX plus Y is the basic operation that's done there. And then there are also things like dot products and norms which are computed. So those things have to be optimized. And again, the optimization should use whatever is the best implementation of those vector operations on a given machine. And I'll point to things from MKL or from AMD Live or from NVIDIA has library routines for doing these things, and they should be heavily drawn on. Also, message passing is done, and you have to do a good job of message passing. And again, you could select the correct message passing library to effectively pass messages around, I'll say.
So it's kind of, I mean, it's not all that different than what you're doing for HPL.
It's not, and it's maybe even simpler because you don't have as many directions to do the optimization. The blocking is not quite as important in this particular case.
And one of the ways that you first explained how these two benchmarks should be thought of really stuck with me. You talked about them as bookends, that HPL is going to exercise your system and show you the very best it can do, whereas HPCG is going to exercise your system and pretty much show you the worst it'll ever do.
Yes, that's a good way to phrase it. The situation, as you say, I refer to it as bookends, where the HPL is the fastest performance that you're going to be able to achieve on the machine. And for most applications, that'll be the very top end. And HPC will be at the bottom end of performance. And that sort of encompasses the range. So another way to think of it is this. We have a number which we think of as the theoretical peak performance of a machine. Mm-hmm. You're never going to get that number. HPL will probably get around 70 to 80% of the theoretical peak performance. Mm-hmm. You could get a little higher, but that's rare. And then there's the HPCG. And with HPCG, you're only going to get a few percent of the theoretical peak performance.
Yes.
And if you get above 3%, you're doing pretty good in terms of the theoretical peak performance of your machine. So that's sort of the bookends, if you will, for the results. And,
and that's a great tip, because these students will know the R peak of their systems.
Yes.
And if they're getting in the 70s, approaching 80, that's fantastic. And if they're getting, approaching 3%, that's fantastic also on the other side.
That's right. So just as an example, the fastest computer, the machine called Fugaku in Japan, it gets about 3% of the theoretical peak for the HPCG benchmark. And I'll give you another number. The Summit supercomputer gets about 1.5% of the theoretical peak. So you see the big drop in
big differences in efficiency, but the Fugaku is, I don't know, I would call it custom designed in a lot of ways. It's not using commodity parts.
That's exactly right. So the Japanese machine was designed to do high performance computing, where the Summit computer was using processors and accelerators, which are of a more general purpose.
Yes. Yes. And I just can't wait for this competition to kick off in earnest and to see what kind of numbers these students do and see their configurations and things.
Yes, it's always exciting. I've been to many of the ASC Student Cluster Challenge competitions. It's always interesting to see what they do and how they do it, and to look at and to observe the intensity that they have in putting together the benchmark results, not only for HPL and HPCG, but for all the benchmarks that are run.
Yes, that's probably the most intense competition. That's the Asia Student Cluster Challenge. Yeah. And that is incredibly intense, but we're going to have some intense times as well. And I just want to thank Dr. Jack for taking the time to explain all this stuff. I don't think you've ever done this before.
That's right, Dan. I've not done it with you anyway.
Yeah.
To this level, yes.
And it's very helpful. We're going to be using this for years in all of the student cluster competitions. So thank you for your time. Stay safe, stay warm out there in Tennessee. And thank you for doing this. And thank you all the students for watching it. Watch it again, learn it, live it. This is what you're going to be doing. Talk to you all soon. Bye-bye.